Hello. The internet has a new favorite research paper. It is this absolute zero paper. People have been going crazy. The most significant paper 2025 from Kyle Corbett. Brilliant idea proposed in the paper. Matthew Berman made a whole video about it. This paper points to an incredible area to work on. Most consequential paper of the year. Quite impressive. Everybody's been talking about this paper, but what they haven't really been talking about is what the paper says in a lot of detail. And I think it's a really interesting paper, but there's also a lot that I do not like. Specifically, I have a lot of problems with implementation. There's a lot of negative signal in their ablation that their core thesis might not have worked at all. So I want to take a few minutes to walk through what this paper is about, which parts I think are impressive, and which parts I think are actually not impressive. I think that these completely rosy takes that are just like, this is the best paper ever, this is not my reading of the paper. I don't agree with this perspective. So let's get started. What is this paper? Their claim here is in an RL environment, when you're trying to get good at a task, the same model should be able to propose problems, solve those problems, get a reward signal of whether you got it right or wrong, and then propose the next problem. So the thing they're really fighting against is this concept of, even though we're in an RL world, a lot of people are still using these known data sets, like all caps math, as the question answer pairs that they're running reinforcement learning against. Or you're taking LeetCode problems, which are already known LeetCode problems, and doing reinforcement against that. And they're like, that's not scalable, that's not general. We really want a paradigm where the model can both propose and solve its own tasks. So, really interesting idea, and I find the theory section of this paper really convincing, and I find the implementation section really unconvincing. So you see here, there's two things. They say there's a paradigm called absolute zero, and then there is a actual instance of this paradigm called the absolute zero reasoner, which is a code writing agent software. Okay, so let's get into it. Here is the main loop they propose. What happens is they have one language model which has two modes. You prompt it. It's either in proposal mode or solving mode. The proposer comes up with a problem. The solver receives that problem and tries to solve it. And then the environment tells you whether you solved it right or wrong. And one thing we should clarify that they say here is we're starting with this RLVR domain. So we're assuming that we have a verifier, which can tell us whether we're right or wrong about anything. And then let's just worry about the binary classifier case. So we're either fully right or we're fully wrong. There's no partial credit. So the two things that this is really obvious for is like math and code. Your software either, LeetCode is either correct or incorrect. Okay, so I mean, this model is, I don't find this diagram that easy to parse. You have like two different environments, you have two different models, you have two different policies. So I want to ground what their contribution is within the context of our standard RL loop. So here's our standard RL diagram. We have our agent who takes actions in the environment. The agent then can observe changes to the state and optionally get some reward. So let's map in all of the parts that they have in their paper. So again, because we're dealing with verifiable rewards, we have a fixed function verifier. So our solver comes up with a solution. The fixed function verifier tells you whether you're right or wrong. Then the solver gets a problem, solves it, and you go in this loop. Now, the whole reason that we're doing this and the whole power of the fixed function verifier is the generator verifier gap. The easiest way to understand this is think about any NP hard problem, like traveling salesman or Sudoku, right? So just like when you come up with a solution, it's really easy to tell you whether that solution is right or wrong, but generating good solutions is a much more difficult problem. So if we can leverage a verifier to learn a really hard function of coming up with solutions, that's arbitrage, and we will take it. And that's kind of like the basis of why this is so important. Okay, so let's go back to our diagram and ask, this sticky note over here, here's a problem. The question is, which problem are you giving the solver? That's the core here. How do you pick which problem to show? And, they come up with this concept of you have a proposer LLM, which picks problems, and then the solver, which solves them. So I'm going to redraw this diagram still with the solver having our point of view. Our solver is the agent. So in this paradigm, the proposer, from the point of view of the solver, is still just part of the environment, right? The solver is just like, I'm an agent. Everything that's not me is the environment. So the proposer comes up with a problem, right? Brings it out of the environment, gives it to the solver. Solver has a solution, run it through the verifier, reward signals whether you're right or wrong. Now, this isn't strictly theoretical, but I claim one way you can look at the role of this proposer is which part of the environment are you spawning in? And here's how I'll illustrate it. Pretend that I have a task which is play Minecraft well. There's different parts of Minecraft, and it's a big environment, and I could put you in different parts of the game. So if you're not very skilled, I'm probably going to put you somewhere calm, like with the trees or the pigs, right? If you're more skilled and you have more complex things, I might get you in this farming environment. And if you're really good at the game and you need to be challenged, maybe I'll put you in a really challenging part, like with all these enemies around in a very confined space. Okay, so the way I'd frame it is our environment is really big. And which part of the environment you're sampling, right? Where in the environment you're placing your agent determines how difficult things are and the kinds of things that it can actually learn. An alternate example to the Minecraft one is this example of a math textbook. So I want you to learn math, but depending on how skilled you are to start, it'll depend which textbook I give you, right? Do I drop you into Algebra 1? Do I put you directly into calculus? Do we go straight to differential equations? Right? It's all part of the environment. The environment is all math problems that exist, but where I put you in that environment, which part of the domain I place you in matters, and it will affect what you can actually learn. So we can just relabel with our math concept. Our proposer chooses which homework to give you. The environment gives you a state which says, here's your homework. The solver tries to solve the math problem. We run it through Wolfram Alpha or whatever you want to call your fixed function verifier, and then you get reward, right? So I'm still going to frame it as among all of the domain of math, where in that environment are you going to situate your agent? That's my way that I will read the proposer. You could read it other ways, but that's my interpretation. Now, since this is a learned function, let's talk about how you reward the proposer. So early on, they say they want to define tasks that maximize learnability. And it's a really interesting concept. How do you maximize learnability? But I really like the way they do it. In my perception, the reward they give the proposer, I think, is the strongest part of the whole paper. So it goes like this. The proposer gives you a problem. You hand it off to the solver, and you have the solver have n shots at solving the problem. Then you take, and you get a 0 or 1. 0 if you get it wrong, 1 if you get it right. You sum up all the rewards, divide by the total, and now you get the average score, the ratio that you got it right or wrong. And this is kind of vaguely reminiscent of a GRPO concept, right? It's you run it multiple times. You just have stochasticity built into the model. So among a group of runs, some of them will have relative advantages over others. Okay, the question is, when you get these results back from the solver, what made it a good problem? So I'm going to break down this a little bit more than they do here. So let's go through the different cases. Let's say that our solve was 0. That means in none of your runs did the solver ever figure out the answer, which probably meant the problem was a little bit too hard. So if you're never going to get it right. It's probably not very useful to assign that problem as homework. Okay? Now, let's say that rsolve is 1. That means every single time you run it, it always got it right. Probably it was too trivial and also wasn't a good homework problem. But now let's say you're between 0 and 1. You're sometimes getting it wrong and you're sometimes getting it right. What do you want to optimize for? So they say the best problem to propose is one that you can just barely get right. They want the lowest solve rate possible that's non-zero. If you just got it right once out of your n tries, it's the perfect frontier problem. It's the problem that, like, if you try really, really hard, you can just barely get it. It's pushing you to your limit. But other than that, every instance of which it gets easier. You know, if you can solve it half the time, or if you can solve it 99% of the time, those are worse problems, right? You want to aim for the problems which is super, super hard but can just barely be solved. They think that those have the most signal, and you're going to train your proposer, 1 minus rsolve, to reward it based on how hard can it make the problem such that the solver can just barely solve it. And, you know, we can have different theories about what maximizes learnability. You know, what's your zone of genius? What's your, like, you know, it's like comfortable enough that you know things, but hard enough that you're like just past, you know, we can debate that. But I would say as a basic heuristic, I think this one's pretty good. You know, I think that the concept really holds. Let's go through some interpretations. In a video game design, you want to make the level just hard enough the player can barely beat it. As a math tutor, you want to pick a problem hard enough that if they really try, they can barely solve it. We are trying to find the edge of the learner's skill level. And I think this is a really nice general framework. So I really like this part. The proposer's reward, and I really like, in my version, I really like thinking about it as the proposer choosing which part of the environment are you going to put the learner into to match their skill level to maximize what they can learn. And I think that's expressed well in the reward function. Moving on to the parts I don't like so much, what I consider to be the red flags of the paper. And like I said before, this is where we move from the theory into the actual implementation. So they implemented one of these things that was working with code. And here's my big problem. They did this ablation, and in the ablation, they tried to not train the proposer at all. See this row that says train solver only? That's the important one. Let's read this. Finally, we consider a case where we do not train the proposer at all. Instead, we only prompt it using the current learner and train the solver alone. We observe a moderate drop in performance, suggesting that while proposer training is beneficial, it may not be the most critical factor for now in the AZR framework. My read is the proposer is the important part of their paper. They basically say in the intro, we're going to take reinforcement learning with verifiable rewards, as popularized by like Tulu and Allen AI, and we're going to add this proposal step because we think proposing your own tasks should help. You know, that's like the basic claim of the paper. But you can see here, the code number, it only goes down by like, what is this, 0.4? The math does go down by like 2 percentage points, but I don't know, it's hard to make claims about this out of distribution generalization. It's like, you don't have any strong theoretical claims, so it's like, I don't know. It doesn't look like, if you really believed them that the proposal system was so powerful, then this is really not supporting that claim, in my view. So our reasonable next question is why not? What went wrong? Why is the proposer not more useful, given that the theory sounds so good, right? You'd want a tutor that picks the perfect problem for you to maximize your learning. And I have 2 different conjectures as to why I think it might not have worked out the way they wanted. The first one is, you know, maybe it's more important that you just do a lot of homework than that you find the perfect homework, you know? So we have this theory that like, oh, you want to find the exact optimal problem that matches your skill level and maximizes the frontier that pushes you the most. But it's like, I don't know. Maybe it's not that important. Maybe as long as you just have a mixture of difficulties, it'll all kind of even out in the end. And you don't need to be so specific about which one you give at which point in time. The other theory is not a theoretical one, but it's just like maybe their implementation was bad. Maybe their proposer was bad. And from what I've read of the paper, I think that this second one is very likely to be the case. I don't have a ton of confidence in their proposer. And I'm going to make some theoretical claims that training a proposer is genuinely a difficult task. So let's start with the first claim. Where I kind of come from here is pre-training. So we've seen these theories that's like, oh, what if we start by training LLMs on textbooks, and then after they learn the textbooks, then we'll level them up to harder textbooks, and then we'll level them up to harder things, and we're going to make all these complicated curriculum to kind of like guide the learner along each step of the way with what it's ready to learn. And perhaps that's more efficient and like faster, but if you don't care about the cost and you don't care about the time, I think we've seen if you just mix up all the data in a pre-training corpus, it'll probably still work out in the end. Because, at every point along your training run, you have a mix of easy and hard problems. Maybe in the beginning of the training run, you're paying more attention to the easy problems, and maybe toward the end, you're paying more attention to the hard. But because you have this data mix, it's not like strictly necessary to split it up and pull all the easy problems at the beginning and all the hard ones at the end, because you're not trying to like match the training dynamics with the data set curricula. All you need to do is be like, we're going to learn the joint distribution. We're going to be able to solve easy and hard problems as one big joint distribution. So I'm not going to worry about the order. I'm just going to call it all. You're going to learn the superposition. So that's one theory, that like maybe this whole concept of we need to find the perfect thing to find the frontier of the learner, if you just scale it up and show it a ton of stuff, you can just use a more basic mix of data, and that's fine. Okay, that's theory number one. Theory number two is the proposer wasn't that good to begin with. And one claim I make is the proposer function is kind of weird, because the correct proposer is always conditional on the current learner. So let's go to the tutor example, right? Let's say that I'm a tutor and I assign a student homework, and then they go and they work on it at night, and then the next day they come and I have to update my priors as to like what I think they've learned the previous night and how they've changed from the last time I saw them, right? The learner's capabilities are always changing. Every batch the learner should be like adjusting what it's good at, hopefully all moving in the right direction, but who knows? And as the proposer, I have to continually catch up and be on the frontier. So we have these training dynamics between the two functions, right? If you think about like how difficult GANs were to train, because if your generator or your discriminator gets too strong and the other one can't catch up, and when the generator changes, the discriminator has to readjust to what the other one has done. I think we have a lot of these same dynamics. It's not like you're trying to learn some objective function. It's not like you're trying to learn the superposition of among all learners what would be the ideal proposer. You're always trying to match the current learner, which means you're always kind of trying to play catch up. So that could be really hard. Or rather unstable. So one thing that I was reading and I found really interesting in the appendix here is when they talked about, right here at the bottom, we briefly explored different strategies for sampling reference code, ultimately settling on uniform sampling for its simplicity, though we also experimented with recency-based sampling and observed potential collapse. So what they're talking about here is the proposer's coming up with Python programs, and they give a few shot examples of other Python programs that happened in the experience buffer, like that happened in the past. And they're saying they just uniformly sampled from programs from the past. And when they tried to bias it toward things that happened more recently, they observed potential collapse. I don't know what collapse means, but one way to read this is that the proposer can be influenced by the few shots that it's seeing in the prompt. And that's not what you really want to see from an RL paper, right? In an RL paper, hopefully it's learning some underlying function and it's encoding that in its weights. And if it's so changeable that just changing kind of which few shots it sees in the prompts can cause the whole thing to collapse, like, what's your confidence that you've actually built a robust proposer instead of just a proposer which is responding to whatever prompt it happens to see, right? Like, how do you know your proposer is actually proposing anything that useful? That's one theory. I don't have strong evidence. It's definitely conjecture, but I am very suspicious of how powerful their proposer actually is. Another intuition I would give to kind of this whole concept of this ablation is, I might claim that in a complex domain, proposing difficult problems is really, really hard. One example that comes to mind is, think about if you're a tech company and you're trying to come up with a good interview question. That's actually really difficult, right? What you're trying to do is propose a question which is exactly on that frontier that candidates who you consider to be high quality candidates can pass it, and candidates that are low quality candidates wouldn't pass it. And just think about how difficult the industry has found that problem, right? Proposing a good interview question is really, really hard. Way harder than solving the interview question, right? So maybe in a domain like writing code programs, you could argue that coming up with the correct frontier for exactly how hard something is, maybe that's genuinely difficult. And, what if you give 4 times the amount of compute to your proposer as to your solver? I don't know. If you think that proposing is such a difficult problem, you might want to do that. Right? But if you kind of go the other way and you're like, no, we don't want to propose the perfect problem. We actually want our solver to just learn the joint distribution or like the superposition among all problems that might come up, then you might flip the entire other way. You might want to give all your compute to the solver and very little compute to the proposer. Maybe it's not important to train this perfect proposal system. I don't know. I think there's a lot of open questions here. So here's how I'd wrap up. I really like this theory about, like, in our RL diagram, you have a broad environment. There's lots of things that you could try to solve and try to improve at. And the question of which part of the environment, which part of the domain you're working on seems like a really cool question. In addition, I really like their framing of this reward. I think this reward makes a lot of sense at trying to find the frontier, right? We've already talked about, though, that I'm not super confident in their implementation. The ablation looked like their proposer didn't have as big an effect as I would expect. I'm not confident the proposer was learning anything useful because of the hinting at collapse when you change the few shots. And, because the proposer is conditioned on the current state of the learner, I would claim it's maybe an unstable training procedure altogether. Or maybe the proposer is just really, really hard to train because, like, coming up with the perfect question might be really, really difficult. But I think the generator verifier gap is a genuinely powerful area to work on, right? Because we can verify easier than we can generate, it does prevent a genuine arbitrage opportunity for self-play. So I think that even if I have problems with the execution, the theory still holds. And I still think that the concept of this absolute zero paper should hold up in the long run, even if their absolute zero reasoner doesn't. So, this is one way to frame the paper. I know that other people are probably going to have very different takes, but this is my read, and especially my issues. I really haven't heard anyone else talk about this ablation problem, but this ablation looks really bad to me. I gotta say, like, if I was on a research team and my main thesis had an ablation that looks like this, I would personally be very disappointed with our execution if I really believed in the theory, which I think the theory makes a ton of sense. So let me know if you read it differently, if you read it the same way. Definitely open to other perspectives. I want to put it out there because I thought it was a really interesting paper, but not all rosy, like I've been kind of seeing some other takes. So let me know what you think.